everyone. It is the libhal bi-weekly meeting. It is March 25th, 2025. Let's get started. All right, so for the agenda today, we're going to go over some new API docs that I've been working on for the last week. The cool thing about these API docs is that they are per package or per package version. This will be very important into the future as we add more features and also maybe even remove some features between major changes. We now have a way to look at the old APIs and the new APIs. And I'll show you that right after I go through the rest of the agenda. Next, I'm going to go over a couple of the list of hard problems. One reason, because we've actually gotten through quite a few of them, but also to look at some of the other ones and to even discuss some of the reasons why those ones are a bit hard. Also, we're going through today and updating the legal notices. I'll talk about that in a sec. I wanted to talk about the design of peripheral managers and why they are the way that they are. And more also just showing you examples of what I mean by a peripheral manager. I think just having a bunch of pictures and kind of showing you how things kind of and describing them, I think will help a lot. Also, I've been experimenting with LTO. I didn't realize back in the day, not like a while back, I tried experimenting with LTO and I had a lot of problems. Usually LTO deleting APIs or functions and stuff like that I actually needed, like the start function and the reset handler. But with PicoLibC, I just thought maybe it's a newer version of GCC, it'll probably just all work. And yeah, it just all works. I had to figure out how to do the right flags to get it to all work, but overall, LTO seems to be well supported in ARM-GCC, so I am actually very interested in adding it. I'll talk about what that means later on. And then finally, I want to go over tracked pointer. Tracked pointer is not something that I've implemented yet, something that I do want to implement, but really this is just a headcanon, just what I am. If I had this thing, would this solve my problems? And I feel like it can, but we'll talk about it. All right, so first, let's talk about the packages. So from here, I'm actually just going to go over to some documentation. Now, I actually modified this a little bit. There used to be a libhal big picture here. The reason why I modified it is because I think I like it without it. I just did it from inspect elements. Also, if you click on this, it goes straight to the image, which is not what we want. So yeah, here you can see all the different interfaces that you may want to interact with or look at. We have all the different errors and documentation on them. So you can read up the documentation and all that and what everything does, use cases for certain things and all of that. You can look at accelerometer and see what it tells you about the APIs here, not very many. For PWM, we also have stuff here, although I think this is missing PWM 16 and PWM channel 16 and also, what's the other one we're missing? PWM group manager. So, but yeah, most of the things that we have available are here, and I'm also working on different ways to make it easier to auto-generate this stuff. So yeah, so you can go here and check this out. Now, the other really cool part about this is that we also have version control. Anytime we release a version, it'll kick off a CI workflow, a CI action, a GitHub action that will clone our repo, build the documentation from the repo's documentation files. I'm not going to go into the details there. But we basically use Doxygen, Sphinx, and Breathe, and then also another theme. There's a stack of things that we use to generate this documentation. I built a Python script that would basically run through all those steps for all the builds, for the build, take the release number, and basically generate a commit and a PR to the API directory. So to actually access this, the URL is the typical libhal GitHub IO/API. So there's a repo that just stores all of our API docs. I thought after spending a week on this, I realized that I wanted originally to put the docs for each repo just separately in their own repo, but that just became a little bit annoying to deal with. Also, I was concerned that there'd be a point where I may want to have the website for libhal's repo and other repos do something else, do something maybe even useful. So having it crowd out the doc directory and stuff like that seems a little bit interesting. Also, I think having just one repo with every single bit of documentation available has another really awesome benefit. Actually, two benefits. One, you have everything in one place, but two, it doesn't make checking out the repos take a long time. There's a lot of files in the API docs, and it would be a shame if most of the files in our repo were just the API docs. If you looked at it by percentage, I thought that was just, and also the fact that downloading all of them and cloning the repo would become obnoxious. So yeah, that's pretty much the whole game plan with these docs. So you go to API, then you do your repo name. So it's just going to be like, in this case, RMMCU, and then your branch or your version that you're looking for. I'm going to go back though real quick. So we have 4.10, and we can go to 4.10. There's nothing actually different between 4.10 and main. They're pretty much identical. There is 4.10.1, and I'm actually, at some point, this is really a laziness thing. I need to actually trim the version so it's just 4.10 and no extra patch number. The reason why is that the patch shouldn't change the API. It shouldn't be a new feature change. It should just be a patch change. Therefore, those other numbers are not necessary. I also should make sure that we don't push out a new PR if only the patch number is changed. So those are just extra things to add to the functionality of the docs. But right now, this seems to be working just fine. And I'm okay with wasting space on Microsoft's GitHub repos until we get to a point where we really do need to start trimming this down. So yeah, that is libhal, and then we also have one for util. This one should be mostly everything, or mostly everything. We might have some things missing here, but it should have all the things that we mostly need. And then we also have the version control for that too. There's only one version because we just added this recently, and we technically cannot backport this, mostly because we don't have all of the appropriate markdown files. And I'm still looking into how we could even do that, but yeah, so it's not backportable. And then over here we have ARMMCU. There's very little here, just DWT and the LPC40's ADC API. I just wanted to experiment and just make sure that the whole flow worked, so I didn't actually add a lot of the additional markdown files to support everything. So yeah, that's the API docs. That's what they look like. This search should do something. I don't know. ADC. Okay, so we're finding all the ADC stuff. Cool. Yeah, looks like it's doing the thing. So yeah, looks like it works. Yeah, so that's the API docs. Let's get back into it. All right, so now let's go over to the list of hard problems. Okay, so there are a couple of problems that we have already resolved. One of them is the API doc version control, which I worked on yesterday, or the last week. Polymorphic catch, also something that I'd worked on. This is something that I just needed to make sure I could do in order to be able to do my talk on exception performance, because I need to be able to prove that polymorphic catch is deterministic. Another one is dealing with halting drivers. So what do you do in a situation where you have to wait for IO waiters, and then also chem message filtering. And all of these came from talking with other people, except for maybe the top one. All these other ones were things that people wanted and people were interested in. We already had ideas of what we wanted to do, and I had actually asked some people here and there for like their suggestions on how we should go about doing it. So these are all like group efforts, even though like if you look at the commits, a lot of them show me there, including getting the validation from students and other people that the CAN messaging filtering scheme made sense. So yeah. Now for some of the unresolved hard problems. We have USB enumeration architecture, which actually we've figured out for the most part, but we just need to actually put it into action. And then once we actually put it into action and really push it to its limits, or at least push it to the area that we think we want to be able to support or reasonably support, then we will say that, hey, this is resolved, but we're pretty much there. One of the interesting things that we have yet to figure out is emulated TLS and GCC, and this is what holds back support for RTOSes. In order for exceptions to work, we need thread local to work, thread local storage specifically. This means that there is an object that is unique across threads but isn't like static, because static would be like only one of this thing for the entire program, whereas thread local is you have only one of these things per your thread. The way that GCC does TLS is kind of weird. I might actually look at it tomorrow just because I've been thinking about it more and more. But yeah, without the support, we can't throw exceptions without having the exceptions conflict with each other. There is a way to get around it. We could have uh, yeah, there's some workarounds. Like I'll give one idea. The exceptions, the exception mechanism needs to be aware that FreeRTOS is being used. So there might be some like something that we have to like hook into. We add some sort of hook. Um, Maybe some way to store the current exception pointer into TLS. Uh, and that way for FreeRTOS, we can still recover it without actually using TLS underneath, or like using thread local, the keyword, because that would be where we'd have to do some emulation. So there's like ideas on how we can approach this. We could either say, hey, we're not using GCC's TLS stuff, we'll just implement it under the hood and tell people not to use thread local. But it would be nice if thread local also just worked. So figuring that out is just useful in general. Next up, we have display interface. The display and storage interfaces actually aren't that hard. To make a trivial version of these, it's quite trivial. You can have a pixel function, and you just you put in the x and y coordinates, and if you're beyond the coordinates of the display, it does nothing. Um, Storage, read and write functions, then that's all you need. But in reality, these are a lot more these are far more complicated than that. Storage isn't usually just a array of bytes that you can update. Usually they're in blocks, and displays have a variety of color codings. If we want to be able to update displays rapidly, we want to work with frame buffers. Hopefully, maybe even two of them, so you can double buffer. The format of those buffers is going to be important. The layout of those buffers is going to be important, potentially important. We might have like our own, maybe we come up with our own, as per the interface, requirements for what the layout should be, and then that affects how some displays work in libhal versus others, and are we okay with that? There's like a lot of things we can talk about that makes these problems like relatively difficult. So that's why these are on the list of difficult problems. And there's a lot more than just this. Technically, lifetimes is another one here. And actually, I was going to put lifetimes on here. And even peripheral managers was also technically on here. I guess I could have put it on the other one. But I think that we're getting closer to a solution there. I'll talk about that later. All right, updating legal notice. One of the items actually on the hard list was just figuring out how to replace myself with the libhal people, just to make sure that was included. And I did some quick researching and basically said, if there's like a person who's pretty much like the primary maintainer and really owner and founder of the project, you can still put their name there. But to make it more holistic, you need to include that you have your contributors there. So the idea here is that everything's Apache 2, and the copyright for any work that you have done is under your name. So it is your work. So if you have a commit that you've made, that is your work. And even though it says that we co-authored it, just because I merged the stuff, I think it's still purely your work, just with my comments and stuff like that. So yeah, so this is just a way to kind of illustrate that the people who are contributors to libhal are also owners of the work that they bring into libhal. And then maybe this name, once we have an actual like legal entity, like a business, we might change this over to the business, so it's no longer under me. But for now, it's just under me. All right, device managers, encapsulating resources. That's what they do. That's the whole point of device managers. Before, we had an object for every possible resource, and we had no way to coordinate them with each other. We could coordinate them with static objects and that kind of stuff. That would, in my opinion, I want to hopefully avoid as many static related things as possible. This will sound very embarrassing and silly once we get to the tracked pointer stuff, because I'm going to be using a lot of it there. But wherever we can choose not to use global memory, we should opt to, just so that we only use the memory that we actually need. And if you had a program that used a lot of resources, but could choose between one or the other application, and if either one gets called, it can utilize the RAM, like the stack, and like if they have a heap, they utilize the heap, what have you. I want for as much memory to be available as possible, and that means putting as much information onto the stack or the heap compared to global, because once it's in global space, you you can't deallocate it. It's there forever. In that vein, um, kind of going away from that, we needed a way for these objects to coordinate with each other. And there are a couple of global ways to coordinate. Like one of the things we talked about 2 weeks ago was changing power on and configure pin to be validation functions. So when you attempt to power on something, it'll check to see if it's already powered on. And if it is, that is confirmation of a conflict. Only one device should be allowed to power on a device to basically have ownership of it. And if something else comes in to do the same thing, then that means contention. Um, um, that is one thing that's external to your objects. But another one is understanding what resources a particular peripheral has and can actually give up. So in this, we have gray to represent our device managers. We have the yellow to represent a item that really only exists one of within this thing. And then we have green to represent multiple of something. Um, each one of these can be tracked if it's necessary. CAN transceiver is one of those interesting ones where you can technically give out n number of CAN transceivers to whomever wants them. And because all the reading is like in a circular buffer and everyone has the same kind of race conditions that they have to consider, and writing technically could be, yeah, I mean, if you did it all in one thread, then it wouldn't be there would be no thread safety issue. So you could have multiple like CAN transceivers or a reference to a CAN transceiver, and they'd all just kind of work. CAN bus manager should only have one that exists around. Technically, you can have multiple because anyone can change the baud rate at any time, but you always have one of those. Same with HAL interrupt. In general, I would probably write the code in such a way that you only grab one of these, and if you attempt to acquire a second one, it will throw an exception. And the benefit here is that you can detect if you've attempted to do that when you really didn't mean to. Because I feel like it's better off to just simply pass this thing around versus calling this API to create multiple instances of an object that may or may not have state. CAN transceiver doesn't have state, but it's not unreasonable for it to have state. So that's why having multiple of these could be a problem. Over here, we have the masks. And we have mask filters and ID filters. And there are, I forget how many of them, but there's an absolute load of them. So the software basically has to do the job of looking through all the masks, seeing if there's any that are available, and then giving them out to whichever caller called for it. And throwing an exception if we run out of masks when the code wants more masks. Here's another example. We have USART. This is, oh, I should have put that in here actually. There's no example of this, but basically the USART peripheral for STM has, it's a normal UART, but also has synchronous. It has a clock signal that can come out as well. This thing can be an old school serial. It can be a zero copy serial. In the future, we may have an interface for the LIN protocol. If you don't know what it is, don't worry. It's basically a protocol. I think it's a single wire protocol that's half duplex that allows a device to talk to up to 12 other devices. And then infrared data. That's another one that I would love to have an interface for in the future. So being able to support sending and receiving infrared data, these are all things that this thing can do. Now, only one of these can be active at a time. So you basically create one of these and then acquire these. Now, there's no reason why our software couldn't allow for you to create a serial, then destroy it later on and transform it into a LIN. That would be cool. I think that there's no issue there. I want to be able to support that kind of thing if that's something that people think they'll need to do. Next one is timer. Timer is stacked, and I don't think I've even included everything that it can do. But it can be a timer. It can be a steady clock. So it can be a clock, a timer, a pulse capture. Think of this as if you were building a RC servo yourself and you needed to take in a PWM signal and you needed to figure out what the width was. You could use the pulse capture to basically capture the width and then determine what your action should be from that. It has a quadrature encoder, meaning that it has rotation sensor capabilities. And it also has PWM, this should be PWM 16 channel, and this should be PWM 16 controller. But basically, you can have up to 4 PWM channels per timer. So these are all individual resources that can be given up. And this particular timer can coordinate, maybe even have a state variable that knows, oh, you've pulled out timer. Therefore, if you attempt to pull out or acquire a PWM at any point, we'll check this guy and go, oh no, we're in the timer state. Throw an exception. Um, or if you've asked for a PWM controller, you go into the PWM state. If you try to ask for a timer or a steady clock, it'll throw an exception. But if you ask for a PWM, it'll allow you through, so long as you have enough. So the management of the resources is handled at runtime. Oh, and a side note for anyone else who's like watching this on video and stuff like that, you may think, oh, wouldn't it be the best to have this be all as compile time as possible? And to some degree, I do agree with that. Um, I think most things you want to do that for. I think a lot of the stuff is kind of extraordinarily difficult to manage completely at compile time. I've tried doing that in the past, and it works to some degree. It just gets really complicated to write, and I find this to be a little bit easier to write. But maybe as time goes on, our software will become more and more complex, and we'll have to just deal with that. ADC can have up to 4 channels of ADC. And here is how it could be written up. Here's how we have it set up for STM for GPIO. You create a GPIO object, you give it a peripheral ID that corresponds to it. If you give the wrong one at compile time, it'll tell you. So you can't ever actually put in you can never compile a program that has the wrong peripheral value here. All of our objects should check to make sure that they have a valid value. The utility of this is that we can also just take whatever that template value is and store it as a member variable and then use that for powering on and powering off. Oh, another reason why you can't tell if you can have object contention is that it could be difficult to figure out if you have 2 instances of an object in your program and they both live at the same time. Like, that is not knowable. Yeah. And if they're cross compilation units, maybe, but that could also mean that this is the same object, just inline, so it can get kind of complicated. So in order to get out, let's say, pin A13, we can do GPIO A, acquire output pin, and then give it a number. Now, this is cool, and this is how I was telling most people to do things. Then I decided that it actually is really important for us to support taking this object here and passing it into the object directly. Support for the 2 isn't even a style thing. Well, so actually, this one's probably the one that we need to always have. This one is maybe like a little helper. This guy here, if we want to ever allow people to use heap or like make a unique pointer of this thing, you need to be able to construct the thing. And this doesn't really allow you to. You could technically move construct it. So like there's that type of angle. But I really don't like the idea of having to potentially create an object, then pass that over to some like a unique pointer to have possession over. I think that's just, it's bad looking code, in my opinion. It's a point where people can make mistakes. And then if this is way too long for you, because it is very long, you can do decal type A output, and then that's a way to shorten it up. So let's see. Yeah, so this is showing the 2 options. So the automatic variable just on the stack, or if you were using standard make unique in order to make a unique pointer from this thing, then you could put in GPIO manager output pin or output, and then your object here in this stuff here. So typical construction, typical way of using unique pointer. Oh, and the last ones. I wanted to show some other things that were not peripherals. So here's a PCA 9685. It has 16 PWM channels, count them, 16, and it has a single PWM controller for the frequency for this guy. So all of these have the same exact frequency. So this kind of represents that. So if a particular device, let's say, had like half of them supported for one set of frequency and the other one with a different frequency that can run at, then we would separate these out. We'd figure out a way to encapsulate that. My idea would be to, basically you ask for a controller 1, a controller 2, and then control them as appropriate. And then same thing with TLA. You got input pins, ADC, and output pins, and all of these are actually like the same pins, just different modes they can all be in. So having to manage that, I think a manager class is apt for that. And now over to LTO support. So LTO support, I don't know when I'll get this in. I'm going to do a little more testing to make sure it's all good. But yeah, It's called link time optimization. This is, I got really excited about this after I talked to a friend of mine, an online friend of mine. His name's Mark. Um, I didn't realize, and this is me not knowing, just being ignorant about this. I didn't realize that link time optimization basically took your code and turned it into like it's called Gimple, I believe, for GCC. And then I bet for LLVM it's something slightly different. I'm not sure if they're all compatible with each other at the LTL level, but basically it creates a representation. It doesn't normally with object files when you compile your C and C++ code. It basically compiles it down into assembly with a couple of extra metadata so that the linker can do its job. With LTO, it basically keeps a lot of information about, not exactly about the source code, but about different things in the source code, such that when you actually go to link everything, it has full knowledge about everything. So it can see, it, like let's say you had a function that you used LTO with, you can have a function that's that's another compilation unit get inlined in other compilation units. So it effectively allows the entire program to be optimized for performance and speed without having the limitations of translation units. It also technically turns any build you make when you link into a Unity build. A Unity build, if you have not heard of it, is basically a strategy with C and C++ where you basically try to build every single source file all at once. So imagine you take all your source files, concatenate them all together, and then run compile. That should technically work because of the way that includes work and the way that includes work, which is like just pasting things, and the way that C and works and all that should just simply do the thing. Can make your compile times longer, but you get some really cool benefits. I did some quick tests this morning, and binaries that were 41 kilobytes went down like 3 to 5 kilobytes. So I saw some like 36K, 30, yeah. Basically, it reduced our code size, and could also open us up to a world where if your binary has LTO support, but still has some way to obfuscate the actual sub software, we could potentially use it to acquire information about the library in order to detect exceptions and where they're propagating from. So a lot of excitement when it comes to LTO. All right, now for my favorite part of today's talk is basically the tracked pointer. I don't know if this is actually a good idea. Maybe it's actually a bad idea, and I am trying to solve a problem that maybe is just not meant to be solved. But I thought I would at least think about it and try to see if I can come up with something useful. So here's the before and after. So we have our LED class here. It has a constructor that takes an output pin by reference. Get the pointer out of that, put that into my output pin pointer. I just realized that there was some old code that actually had this as a reference, which is actually a problem because it causes the move constructor to no longer exist because you cannot reassign references. So that's a problem. That's the thing. There's like you can kind of get away around that, but it's in general, just keep this as pointers, makes your life a lot easier. Don't store as members references unless you want to deal with that. Usage of this particular pointer is just arrow operator, do the thing, arrow operator, done. Perfectly fine. For tracked pointer, it is identical. Just you wrap it in tracked pointer. If you've used a unique pointer before, it's basically the same semantics. It should just operate like a typical pointer. So if you were going to move your code over to it, it should be as simple as taking all your pointer types, removing the asterisks, and then covering them in how tracked pointer, and then making all of your inputs for your constructors also take tracked pointer. In order to create a tracked pointer, you can't just like fabric one of them out of nowhere. You have to get it from a tracked object. So here we have some custom output pin. This could be like your pin for your RP2040 or for your LPC or from STM or whatever. So you have some output pin and it is tracked. This is the full implementation with all the memory incorporated there. This is on the stack, no heap allocation required. You pass pin into your little blinker LED object, you hit toggle, it does what you expect. The tracked class implicitly converts into a tracked pointer. And in doing so, stuff happens. I'll go get into that in a little bit. But the idea is that you should be able to pass this as if, just like how you'd be able to pass objects that are references or pass by reference. So, and that's really your only real way to create these. Kind of like how you can't, well, I guess you can always just create a reference out of nowhere. I guess you can't easily fabricate a reference without having another object that you're trying to reference. So that's kind of that's the semantic that I'm trying to work with. Now here's to kind of illustrate how this can go wrong and how tracked pointer can help us, what it can do for us. So we have our tracked output pin, we pass it into our LED, we toggle it, then we return it up one level. From here, the obvious thing is that this guy it basically has a reference, like this LED, this blinker guy has a reference to pin, and this is gonna break it. The next kind of slide kind of shows this destruction of this guy turns back, this thing's now invalid. So in order to kind of show you why this is, it's still a problem, but it's all well defined, and we get a proper exception when this happens, when this lifetime violation occurs. So here's what we've done, or here's what I've done. I've come up with this thing called tracked TN. So you didn't see it over here, but the N is set to 1 by default, so each object that you make that's tracked gets a single reference of it that can exist. The idea of tracked is basically to wrangle and control pointers and to ensure that tracked pointer always points to something valid. It is never pointing to something that's invalid, because that's annoying to deal with and it's hard to debug. So we're going to make sure that tracked pointer is always pointing to something that is valid. And it takes a little bit of work. So with tracked, what we actually have is this kind of nesting of objects. So our T is allocated here. The tracked object owns the memory in its entirety of the object that it's trying to create, that it's going to be an instance of. So the memory for it is stored within the tracked object, aligned appropriately. There is 1 word or 4 bytes worth of information that is also added to tracked for your object. So inside of this is actually another thing called a tracked object, which includes some metadata and a 3-byte capacity. And what's 2 to the power of 24? Like 16 million. I had someone that I spoke to told me that they have objects in their simulation software that has a single object that could have more than 2 to the power 32 references to it. And I was like, that's 32 gigabytes worth of just pointers in your program. He said, hey man, the stuff I work on is crazy. But I don't think we're going to be dealing with that anytime soon. I don't think we need that much memory for this capacity. And if we find out that we really need one, maybe we'll make a fat tracked in the future. I don't know. Hopefully one that is backwards compatible. That would be my number one requirement. So we have some metadata here. This will include, we'll try to figure out what we're going to put there. At first I was going to put in the lifetime information of this guy, such as whether or not it's static, which I have a way of solving that without needing to do that. Whether or not it's static, dynamic, or automatic. And the benefit of that is maybe some object can determine how it should operate based on that information. Oh, actually, here's one. If it's dynamic, because I actually want tracked and tracked pointers to work with heap as well. So you have a make tracked, which also heap allocates your object for you and returns back a tracked pointer. Also, with that, you can copy tracked pointers around, but the amount that you can copy them is limited to a registry. But yeah, basically Meta would just be able to know oh, it works like a shared pointer. So if all the tracked objects are gone, it should deallocate the memory. So within tracked, we have the object that we want, we have a capacity, and we have this metadata. And right over here, we have these, I call it the registry. And these are basically an array of the pointers to tracked pointers to this T, to this thing here. Here's how this thing works. When you create a tracked pointer, it points to the tracked object. And because it only points to the tracked object, and it is just a pointer, it's really just the size of a pointer. When you try to access this thing, it's as fast as accessing a typical pointer. It has the same overhead, which is 0 of a unique pointer. When you create one, the address of the pointer itself is added to the registry of the tracked object. So any pointers you make also have pointers to themselves. This is akin to making all your pointers double-sized, where the thing that you're pointing to also knows where you are. If we made a couple more, then we'd fill up the registry to hold all of these. If you tried to ask for yet another tracked pointer, it would throw an exception. I'm still figuring out what's the best course. Like, if should we do move only? I assume we can do copies to allow for shared pointer-like capabilities. Would also be important for things like iterators if we get there. Although I'd expect the iterators would be like from within the T, not from tracked. I'm not. I'm still coming up with a lot of things here, but this is the main idea. These pointers point to these guys, and this guy points to this thing here. This thing does not know how, like, in order to keep tracked pointer separated from the different types of tracked n, so like it could be n equals 2, n equals 15, n equals 3. There is a separation between the tracked object and like the registry value. So this thing here only has a single template. So you could have it point to a whole variety of different things, but only has a single template instance, which reduces on code size. So just wanted to add that in there. Here's the cool thing. If you move a tracked pointer, it updates its tracked objects registry. So if you kind of look back here, we had 2 0. So we have address 0 not, 1 not, and 2 not. Then we have 2 1. So now we've nothing actually increments here, but we've updated the value of the address to its newest value. So before it used to point to whatever this memory was, now it points to a new location. So as the objects that you pass track pointers to, if they move around, they also move around the registry as well. And here's another example of that happening. So it should always be keeping up with whatever is happening, however your objects are moved. Oh, and last thing I was going to say is, at the cost of doubling the size of our pointers, we can get this other capability. So let's say that the lifetime of this object is invalidated. Like, for example, when we return from a function and we had passed that object ourselves to some other object. Well, what we do is we redirect all of the pointers that we had to an invalid instance of themselves that is statically allocated. It is statically allocated well, actually, I'll go into that in a sec. So the idea here is this all works over polymorphic objects. So we can imagine that tinvalid is actually like an output pin implementation where all of the APIs throw an exception. Basically, it warns the system, hey, something's gone wrong. So in this case, all of the T pointers are pointed over to this guy. And yeah. Another interesting thing is that if you set your n to 0, the way that I'm planning on handling this is that it forces this object to be statically allocated, therefore allowing it to have an infinite number of tracked pointers. So if you were to pass this object to a tracked pointer, thing taken a tracked pointer, you could make one from it because everyone can point to this, but it doesn't need to know about you because it never has to update the tracked pointers. So that's pretty much the idea here. One other thing I'm going to talk about before I go any further is I expect that this will have 0 runtime cost so long as you're not moving anything. All the cost is born during move operations. So once the system has kind of settled, I don't expect there to be a lot of extra things happening, or a lot of extra cost coming from the move operations. Which again shouldn't be too complicated. It's really iterating through a list, finding yourself and updating yourself if you're moving and that kind of thing. Also expect it to all be really nice and generic and like in a single instance or single form. So there's only like a single function that implements the logic to find itself, update itself, or point it and do like the pointing to the static object. So all API calls to tinvalid, which implements some polymorphic base class common to T, should throw HAL lifetime violation. And this is kind of the key. The goal is that if you have messed up in your code and there's basically a bug, that the code will throw an exception relating to that bug occurring. And from there, at the least, we will be able to not allow the program to continue on if it's currently in the area of undefined behavior. And that's pretty much it for these slides. But last thing I kind of want to bring up is just this whole thing. I am concerned about adding this all over the place and this becoming an undue burden on a lot of libhal code. I'm planning on doing a lot of space analysis for this. My hope is that this tracked object with n equals 0 for the invalid case, I can only imagine on a Cortex M4 that the memory taken up by this is 1, 2, 3 pointers, and that's it. So a word for the length, which is kind of shown for this guy here. The T, since it'll be polymorphic, will have the first element will be the vtable pointer, the second element will be the pointer to the RTTI information, and the object will have no member fields because it shouldn't need anything. It should be empty, basically. So all of your tracked objects, for every unique tracked T that you have, there would exist an additional 3 pointers that cost that. So I'm actually going to do some quick math. If I have 16 different unique tracked types times 3 times 4, so there's a bit of a cost here. Just for the invalid objects themselves, the cost would be about, for 16 of these types, 192 bytes. So that's the thing that I am concerned about. There's also the extra cost of just having the move constructors for all these different pointers here. My hope is that a lot of that stuff gets inlined and kind of gets eliminated, or is so trivial that not too complicated. But we'll see. Not as powerful as a compile time borrowed checker, but it basically gives you that kind of capability. Oh, and one thing I forgot to bring up, which I will bring up right before we leave. Basically, this thing is my version of arc, Rust's arc. And if you put a mutex, I want to make a mutex type for libhal as well. So you can basically have an arc mutex so that you can have a protected type. The hope here is that with that, you basically be able to have lifetime invalidation guarantees and also mutual exclusion guarantees. So you should be thread safe and you should also be lifetime safe. That's pretty much the goal. And I think that's possible. And I think once we have those two things, at the very least, even if they're not the most performant way of doing things, we would at least have a safe way of doing things. And I think with everything else that we're doing, we can keep the code sizes relatively small and still be able to do a lot of stuff. So with that, basically, we are done for this week.